like our fancy machines. Yeah. Okay. Very good. So I thought we would continue exploring Qiskit, get more familiar, programming, explore a few circuits, and get familiarized, maybe do a couple exercises if we have time for them today. But before I do, I wanted to clarify the one point which probably wasted more time on than I should have last time, but I figured out what the problem was. It's just the notation in your textbook was a little bit cumbersome. So I've simplified. So we wrote down a matrix for U. Last time, this was the most general. The most general unitary gate, we parameterized by the three numbers. The three numbers are, we wrote them as theta, phi, and lambda. So in the last class, I had written down a matrix, and that matrix was, as I said, a little bit cumbersome to work with. So I simplified it a little bit. So if you look at the matrix from last time, then actually what it's equal to is e to the minus j phi over 2, e to the minus I lambda over 2, cosine theta over 2, minus e to the minus I lambda over 2, sine theta over 2, and e to phi. So it's just some, I just pulled out this, sorry, I started using the physics, the J. And so basically it's just this J by and this can be further simplified. So if you compare the matrix I wrote in the last class to this one, they're identical. But now I pulled out the simplifying factor e to the minus j phi over 2. And it turns out you can pull out one more factor, this e to the minus j lambda over 2. So the total matrix can be simplified as the minus j phi plus lambda over 2 times a simpler looking matrix, which is cosine theta over 2 minus sine theta over 2 e to the j phi sine theta over 2 and e to the j phi plus lambda sine cosine. Uh-oh. Okay. All right, so what this, and if you compare the definition of the unitary gate in IBM Qiskit, it's this matrix over here. Okay, this, and in your textbook, it was this other matrix that I wrote down in the class last time, and as you can see, they're equivalent because there's just a global phase outside this matrix. So the matrix definition for unitary gate in Qiskit and in your book are identical, except that there's this extra phase factor, which we can ignore for our purposes because it's just a global phase. And so now you can write down to show you that all the gates, and so the angles that I wrote down last time were correct, but it was just with the complicated matrix, it was just too easy to make little mistakes in the calculation. So now u of pi 0 pi, which is what I had written down last time, but now will be almost trivial to verify. This is now e to the minus j pi. I'm leaving it for now, but of course, as I said, you can throw it out because it's just a global phase. Cosine pi over 2 is 0. This minus sine theta is minus 1. Then down here is e to the j pi, and that's minus 1 again, minus sine pi over 2, so that's also minus 1. And then the last one is phi plus lambda, which is pi plus pi, which is 2 pi, and e to the j 2 pi is 1. So this just becomes 0. So if I now pull out the minus sign, this just becomes minus e to the minus j pi is I. It is also minus 1. So this is also minus 1. So this is plus 1 times 0, 1, 1, 0, which is identical to the x gate. So that is what we wanted to show, and this is the sort of the verification of that. Okay, now I have to turn on the thing and wait for it to come online. Any questions about this relationship? So it's just to show you. So now in IBM, their U matrix, you can make any matrix you want, any unitary gate you want, with by parameterizing theta, phi, and lambda. That'll be this part over here, and then the other part is not important for our purposes. Oh, I guess it's actually j pi over 2 because theta was pi, phi was 0, lambda was pi. And so that's this one over here, lambda j pi over 2, which is minus I, but minus I outside, so it doesn't matter. The minus I, it should be minus Ix, but as I said, the minus I doesn't take, so. I uploaded several notebooks to your modules. These are basically from the Qiskit textbook or text site. So I thought we'll work through them. Some of this should be fairly familiar and easy for you because we have talked about them quite a lot in the beginning, but I thought it's helpful to go through it at like the single qubit, multi-qubit stage, and then we can come back. So you may remember in the last class, we did the Ramsey X circuit in the class notebook that we were looking at last time. I'll come back to that. But for now, let's just go through the single qubit gates, because I think that can be helpful. Doesn't seem to work. Apple Plus. Is that big enough for everyone to read, or should I make it bigger? Okay, do people in the back can read it? All right, so the starting point is we have these imports just as usual for quantum circuit, but there are two new things we're importing here. The assemble, which is something that we'll use later on. It assembles the circuit into an object. And then we used Qiskit visualization last time as well to import like the histogram. But now instead of importing everything, I'm just importing the things I need. The block multivector, which I'll explain in a minute what that is, and then plot histogram. And of course, feel free, you can read through this whole thing. I'm going to skip a lot of it because we are somewhat familiar with gates and things like that. But I just wanted to show you that this with this notebook, we can like do a lot. So let's just run this first cell over here to. I guess it's. Okay. We'll see if the next one works or not. Okay, so here they're just talking about the X gate, which I think you all know. And now let's, this part down here talks about how we can make our own quantum circuit. So the idea in this quantum circuit is it can have many arguments, but the two arguments are the first argument is the quantum number of bits in the quantum register. And then a second argument, as we'll see later, is for a classical register. So if and then you can see the next line is we're doing an X gate on the 0th bit, 0th qubit, and then we're drawing the circuit. So let's see if that works. Yeah, and that works. Yeah, hopefully it works for you also. And now this is the part I was just mentioning. This is, I think, quite helpful. When I was doing the slides for your classes, I was just using my own code to visualize on the block sphere. But you can come to this and you can also build your own visualizations for the block sphere and the state vector yourself right here. So these are the set of commands. So save the state vector first and then assemble that into an object, a quantum object. And then that it uses the simulator that we had just imported the backend and runs this quantum object, finds the result, and then gets the state vector. And then the last part, which is called the block multivector, well, all it does is, this is for a single qubit, so it's just one qubit. But if you had multiple qubits, then you would need to take the tensor product of all the qubits. So that's what this block multivector does. It can handle multiple qubits, which may be even in an entangled state, but of course, then the block vector will not make any sense, but it can do that. It can handle that state with like many qubits. Okay, so if I run that. Okay, well, it's not really work. Maybe I have to start again. So, I think it's how. Let's just quit. Do you all have any trouble like this when uploading? You have.
It's the same error that you.
Oh, I see. I'm sorry. Okay. Save this file. Okay, okay, then ignore mine. Cool. Let's see if we can find. Oh, this is a good exercise. Find it. Let's say I don't even have that. It seems really slow. Or something. Fine. Okay, all right, so that is the same file that I for some reason screwed up when I downloaded it. I don't know what, I downloaded it from their site. Apparently it doesn't like it. Download and upload it back to their site. Okay, all right, let's start all over again. Can't tell. Usually it should like come back after execution. Seem to be. It's still dark. Over here.
I think it's running right now.
You think it's done?
Yeah, I think it's for like it didn't run or something.
Didn't run? All right, let's try again. Well, it imported quantum circuit, I know that. I see it's able to run that. But this is their own. Oh, oh. Okay. This is their code. So, the fact that it doesn't run doesn't give me a high degree of confidence here. All right, let's try a different simulator, maybe. We know from, I don't think we should have to use this. Or no, actually. Okay. Oh, that's weird because last time this worked. All right, let's go back. Excuse me. I opened my in-class, because that was working last time. Plus, but yeah. Just making sure. Oh, I see. I see. AER simulator statement. Okay. Yeah, I shouldn't have to do this. So, yeah. Yeah, we did this last time, right? We imported all. Okay, let's try executing this circuit. We know this all worked last time. So let's try this. Okay, that works. All right. Okay. See. Okay, that works too. Okay, get back in QASM simulator. Let's try that. Job is successfully done. Okay. So all this works. There's no reason for this other stuff not to work. Working. Interesting. Okay, let me change this to, I will try a bunch of different scenarios. See if any one of them uses a result. Okay, that did something. Please it didn't throw back an error. Try if I now run it with. Oh, now it's fine. Wow. That was weird. Okay. No idea why that didn't. Okay. Oh no, sorry. I'm way up here. Sorry, I need to be done. I bet this will not work. Yeah, same. Okay. Maybe if I try QASM simulator. See if that- Make sure the farm circuit is the same. Yeah, it's the same. That's right. Same alert. Okay. Oh, I'm sorry. This should be working. Okay, that's good. Using a QOps for running differently. As of this date, transfer circuit should not be passed directly using backend buffer circuits. Okay, let's try that. But I guess it doesn't want to use QOBJ. Just run the circuit. Okay, which is what we did over here, I guess. Execute circuit backend. So we can also do backend dot run. So let's try that. Let's try this piece of code. Yeah, we're learning something. That textbook has some mistakes. Okay. Try the A. Yeah. Backend dot run. QC. Didn't throw back an error, at least. Okay. All right, so we have the simulation result. Let's try state equals. So, oh, is it? So not result. Okay, I guess we can just replace all this code here. Let's try the last one and see if this works. Yep, cool. All right. So that is the new code. So let's throw away whatever is in this textbook. Here's all this. This is the right code now that we need. Okay, so let's just clean it up a little, all in one. All right, so we now have the same thing, but now I guess this is the new way to do it. They keep changing things and not updating stuff, which is not surprising since things are moving fast.
You go back, so some, just.
Huh?
I didn't finish, right?
Yeah, sure. This is their copy. Right, this copy says this doesn't seem to. Things that- see. I'm not quite sure how to get rid of this, but yeah, maybe I'm gonna get rid of that for. All right, everybody okay with this part of the code so far? All right, so now we can do the Y and the Z gates. I don't know if this demo is working. It's the same as we know from our earlier explorations. So they've written it as a matrix form, they've written it in the kit algebra form, which we've discussed so many times now, I think. Really not difficult for you to understand why they've written it in these ways. And so now, let's see what this is. Oh, it works, okay. So they say that you can use this to play with the games and it's action on the single vector. So this seems to suit. All right, so now they're doing a Y and a Z gate in succession directly in QuizKit, and you can see you may remember QC already had the X in it. So this was the and this state vector here was just us simulating it here. So simulator got the state vector and then ran Y and Z code. So that's what this line represents over here. Okay, digression X, Y, and Z bases. So maybe one little thing that you probably haven't heard me talk about too much is something called the eigenvectors and eigenstates of the matrices. It's not very different from things we've already discussed. So we know the plus and minus. So if we go back to the block sphere, you know, we've talked about how plus is the measurement along the X basis and minus is the, you know, the other like the 0 and 1, but just rotated onto the X axis. Similarly, the plus I and minus I are like the 0, 1, just rotated onto the Y axis. And that's what this is saying. So those are called measurements in the X and Y bases. And the states that we get, the plus state and the minus state, are called eigenvectors of the X gate. Because what the eigenvector is, actually it's here, so let me just expand it. So an eigenvector is defined by the property that the matrix M acting on the vector V produces the vector V with some constant in front of it. Okay. So essentially, it's like thinking of it as like a scaling operation. It takes an eigenvector and it returns the same eigenvector, maybe with some scaling number. Okay. In our case, we know, for example, that the Z gate acting on the state 0 gives me 0 and 1 gives me -1, right? Because that's what the matrix Z does. Same thing with X gate. If X operates on the plus state, it produces plus again with a plus sign in front. And if X operates on the minus state, it will produce minus with a minus sign in front of it. You can verify this yourself by taking the matrices or just by looking at the action of what the X gate does on the plus and minus states. So plus and minus are eigenstates. Okay, these 0 and 1 are eigenstates of the Z gate with eigen values plus and minus 1. Okay. Similarly, the state plus and minus are eigenstates of the X gate with again the eigen values +1 and -1. Okay, and okay, they have labeled these by the circle. We call it +I in our notation in our textbook. This is for the Y gate. They again will give you eigenvalues plus or -1, and these are the eigenvectors, which is +I and -I in our notation in the textbook and in the lectures. Okay. So, any questions on that? Yes.
So there are like eigenstates and eigenvectors. Could we like use them because like we represent the states of that vectors?
Sorry, can you speak up a little at the last part? I didn't know the question.
Like eigenstates and eigenvectors. So since states are like written as vectors,
Yeah.
we just use eigenstates and eigenvectors. Like, sort of, like they kind of mean the same thing.
You mean eigenstates and state vectors? Do they mean the same thing?
No, just like eigenstates and eigenvectors.
Yeah, eigenvectors and eigenstates are the same thing. Okay. But not every state may be an eigenstate or an eigenvector for a unitary matrix. Okay. Yeah, eigenstate or eigenvector is the same thing. Sorry, maybe I said eigenstate, but it's the same as eigenvector. Okay. Because we know every state can be represented as a column. Good. All right, and okay, this is just exactly what I just said, which is plus and minus are eigenstates of the X gate. It asks you to verify that. It's fairly straightforward. Okay, and then we come to the Hadamard gate. Okay, we've done this before, so I'm not going to go into it again. And then here's another gate demo that you can use, that you can run yourself now. So again, now we introduce X, Y, Z, but also Hadamard. Okay, and we've already talked about this. Hadamard is like rotation around the axis X plus Z in the block field. Okay, so it's a line between the X and the Z axis. Okay, yeah, and I mean, you can play with this. So you see, when X operates on the state 0. It produces the one state and so on. So, for example, if you take the Z gate and operate it, it does nothing. Hadamard, it produces the X state and so on. So, this is just the demo. Okay, and this part, I think, why I wanted to do this part here is when we do the Ramsey circuit, we'll be doing measurement in different bases, and I got a couple questions which made me think that maybe people were still a little confused about that part. So let's go through this again. We have discussed this a couple different times. We discussed this when we did the quantum bomb detector. We also sort of discussed it when we have talked about this a couple different times in just the regular class. But here, this is now, when I tell you now, okay, write a circuit, and now instead of measuring in 0 and 1, I want you to measure along some new basis, let's call it U and V, okay? And the way to do that, how do you do that? Okay, and this is demonstrating that for the X gate, how you can now measure a qubit in the X basis. And the reason for this is, goes back to something we talked about when we did transformations of the basis states, going back to when we were discussing transformations on the basis states. So the idea is that if I want to measure some state psi, right, as let's say it's A0 plus B1, okay, and now I want to write this in terms of some values C0 times U plus C1 times V, okay, where U and V are orthogonal basis vectors, okay. So we did an example like this in the quantum bomb detector case. And the reasoning was that since U and V basically can be written as some U is just R times 0 and V is just R times 1, where R is the matrix, then we want to rewrite the state that's given to us. We want to rewrite that. So this is the state given to us, A0 plus B1, and I want to rewrite it into this form over here, right? Some constant, some number C0 times U plus some C1 times V. And the way to do that is, we know U is R0, which means 0 is R dagger times U. And 1 is R dagger times V. And so that's what we do here. We write this as A R dagger U plus B R dagger. B here. And so this is basically R dagger acting on the state. So when I want to express the column vector psi in terms of or in measurements along U and V, basically I'll take it and multiply it by R dagger, and that will allow me to measure along some new basis UV. Okay, so that's what we do here now in our circuit. Is this clear to everyone? What we're doing here? This is what we would do manually, right? If you remember, we did many examples where we rewrite 0 in terms of plus and minus, 1 in terms of plus and minus, substitute it here, and go through the algebra. Well, this is just the matrix version of that. So this now gives us the coefficients of that C0 and C1 in the basis U and V, which we want. So that is now implemented in code. Here. So now let's say I want to do an X measurement. What this is saying is, if I want to measure the qubit in the X basis and store the result in the C basis, well, we know Hadamard takes us from 0 to plus and 1 to minus, right? As we've seen many times. Therefore, Hadamard is the gate that transforms between the X basis and the Z basis, or takes the Z basis to the X basis. If I operate with Hadamard on 0, I get plus, and if I operate with Hadamard on 1, I get minus. So that's like the U and V that I just wrote down. So to go backward, I need to operate with H dagger, okay, on the state to obtain the measurement along the X basis. But H dagger is the same as H. So I just operate with Hadamard on the circuit at the end of the circuit, and that allows me to measure along the X axis. Okay. So, and that piece of code, you see the nice thing is to define it as a little function so that you can then reuse it anywhere you want. And so that's a good coding practice to get into, as I'm sure you've been told in other classes and so on. So it just operates with Hadamard. So you could write your own, maybe we can now. Okay, and maybe that should be one of the exercises. Why don't we write a function now? So you have this code, why don't you create a new cell? And repeat this code, but now change this to Y measurement. Let's see if we can do that. Copy this cell to a new one. Let's execute this cell first. You all have this cell, I think, right? No? Yeah. So you can execute this cell. There, okay. Okay. And now let's copy this cell down. But now I want to change that to a Y measurement. Now, of course, something has to change here, right? Let's measure this along the Y basis. For the result, CP. So everything is the same, except we have to change this one line of code. Okay. So what should we put here? What do you think we need to do to the basis? So measuring along X is rotating from 0, 1 to the X axis. So now I need to rotate that from 0, 1 to the Y. Now, Hadamard rotates us from 0, 1 to X. So what we need is something that rotates from X to Y. Is there a gate that does that among the gates that you have learned? Yes.
The Z gate?
The Z gate rotates by pi around the Z axis, but you're getting close. So square root of Z, right, basically, will rotate by pi over 2 around the Z axis. Perfect. And the square root of square root of Z has a name. We've given it a name before. It's called, anybody remember this gate? The square root of Z. Something that's when squared has to give Z. Think about it. You can look at your notes. Yes, Alan. The phase gate, indeed. Which phase though? Because phase gate in general can have any phase. Which phase do I want? 90-degree one. Awesome. Perfect. Indeed. So the phase gate with pi over 2 will give me the gate that I want. But remember, we need to take the dagger off, okay, the complex conjugate. All right. Turns out we can cheat. There is a gate that already does that. It's called S dagger, or S. S is the gate, which is the square root of Z. That is S squared equals Z. And therefore, S dagger is square root of Z, which is what, or which gives us the measurement that we want. So we write here. Okay. And so that will measure the qubit in the Y basis. Oh, sorry. And then we need to operate with the head amount again. Right, because we said we need head amount and we need S dagger. Okay, so. Okay, so let's represent that circuit and see what it does. By the way, I forgot to go through the rest of this. So notice another nice thing here is it allows us to initialize the qubit in any state we want with just defining a column vector, just like how we were doing in class. So write down the state. So normally qubits are usually thought of as being 0 all the time, right? And when they start out, okay. And then we operate with some gate and we create the state we want and then we do the rest. But here they're allowing us to just directly write the state in. Okay, at least for simulation purposes, that's okay. Okay. And then initializes the state. So that is this command over here. QC initialize, okay, initial state. And there's the classical register, which is the C over here, is another nice thing I should have pointed out, which is the quantum circuit is initialized with 1 qubit and 1 classical bit over here. So the second number in this function represents the number of bits in the classical register. And then it initializes this into the state where this state is in the initial state given here, and the classical bit, of course, is in the 0 state. Okay. And so the X measurement over here now takes us the qubit 0, the classical bit, and it takes the quantum circuit input and finds out what that's. Okay, so at this point, I think we have. Let's make sure that when we get the final answer, this is what we expect. That did it. Oh, X measurement, that's right. Y measurement. Perfect. Good. All right, and to verify this, well, you will want to verify this somehow, I guess. Let's see. Maybe we should change our initial state to be minus J. Minus J. So now, instead of my initial state being along the minus axis, right? I'm measuring it, and the initial state is along the minus J axis or the minus Y state. Okay. So let's see what that gives us. This J is not different. This one they have minus J. Okay, so I'll just define it, just like I did in my. I have to remember what's going on. Okay, so it doesn't have the numpy. Let's see. It didn't work. Okay. All right, this is maybe not good because of this. Let me see. Maybe I need a complex. I just use numpy in my Python. I don't know. See. So this is the problem that I showed you last time. When we do this with NumPy, everything is like squared and, you get like numbers on the order of 10 to the minus 26 and so on. And so usually I write a little code to like get rid of those extra 26 and stuff, but here it doesn't move. Okay. All right. Investigate this. This must be there. So I just didn't think to. I thought it was the same as NumPy. All right, so we can't right now verify the J, but we'll come up with a way to do this with J, and I'll figure it out. But for now, you can at least know how to measure along the x-axis, the y-axis. Sorry. Okay, so in the next part, they're talking about identities, basically. So for example, this is, fairly, straightforward to verify this identity. I think we did a similar example in the class back in the single qubit stuff. Okay, we know this part will not work, so let's replace it with our. Yes. Yeah, so they're just trying to run the simulator. This won't work. We already have a backend, so I don't need to repeat that. Of course. I guess I need this. Let's check that we have a state vector. Okay. Make sure this is yeah, that's what it is. So QC has been initialized. It has this representation for some reason. So. I see, because we made a measurement at the end, so there's no state vector. Okay, that's no. Result. That one. Good. Pretty good. So we finally managed to fix that. Okay. Let's also run the first one. So what were we expecting? So indeed, right? So if we take this guy and we measure it, then we should indeed get that the measurement result should give me perfect because this is indeed an eigenvector of H, because it gives me H acting on the minus state will give me measurement along the X basis, which is going to give me the one state. So again, if I verify that, I should get the one state with 100% probability, and that's what I get. So actually, let's copy it in two separate places. So we have this result here. So that was Y measurement, or that's the X measurement result, right? So we get one. That's after running this part of the circuit, and then after I run this here. Okay. Now the same QC. Did I change that? No, it's the same. So initial state is still this, except now I operated with this dagger and then measured it. So now we see we get half result, because the X state has half probability to be along plus Y and half probability to be along minus Y, right? So when I measure that, I get roughly half the time I am in the plus Y state and half the time in the minus Y state. This making sense to everyone? Why the two results are different? Okay, these comments were for the X state. We have already changed things a little bit here with the Y measure. Okay, this is the P gate, like Allison said, right? Which is the most general gate, right? Is for a phase gate is the one that does this matrix. It rotates by some angle phi. Okay. We just showed that by applying that for, say, a pi over 2 rotation, we can take us from the X basis to the Y basis, for example. Okay. And here what they're doing is showing you how to create any general phase gate with this command, qc.p. P is the phase gate with a pi over 4 angle, and that gives us the this 0. Oh, and also they have this little gate demo again, I guess. You can see they've added in the H and P as well, so you can play with that if you like. And so again here, you see we specify the gate by one more parameter. Normally we just tell it which qubit to work on, right? When we operate a single qubit gate, we just need to tell it qubit 0, qubit 1, etc., which is what we've been doing earlier up there. So for example, when I called up here, when I called the S dagger, I was just giving it the state 0, the qubit 0. So all it needed was to know which qubit to act on. Okay. But now I also need to tell it what angle. And so the angle is the first argument in this function P, and that's pi over 4 here. That gives me this this circuit over here. So That's the circuit over there. Okay, there are a few other gates. We've talked about some of them already, actually. The I gate, of course, identity, not a problem. S gate, we've just finished talking about that. It rotates as also known as the square root of Z. Yeah, so if you want to look at it, so it's S and S dagger, and so therefore it basically has the effect of like one gate, which is sorry, S and S squared is Z, as shown here, and S dagger is not its own inverse. So S dagger and S are different, which is unusual because most of the other gates we've talked about are their own inverses as well. So S and S dagger are not like that. Okay. Right, and that's done here. Since we already taken an example of this earlier, I'm not going to repeat that. And then the T gate is similar to the S gate, except with the phase is pi over 4 rather than pi over 2. I won't go through that. Feel free to work through that yourself. And we've talked about it earlier process. So, okay, and this is the most general U gate, and you should know now this allows you to make your own U gate, as you can see here, right? So the U gate operator here does a rotation of pi over 2 for theta. In that notation, I introduced theta phi lambda. So pi over 2, and then phi is 0, lambda is pi here. And then, of course, you have to tell it which qubit to operate on, which is the 0th qubit. So that's the notation over here. QC dot U time, and then theta phi lambda, which is all given here. Again, this is the exact same matrix I just wrote on the board at the beginning of the class. Okay. All right. So any questions about all this? So we can go ahead and execute all of these, right? If you want, just go through quickly and execute all of this. We did that one. Let's do that one. And here's the widget again you can play with. It has all the gates basically now. You can like move the slider around to tell you what to do if you operate at the phase gate. On this, when it's around Z, nothing happens. So first, let's do an X. Let's do Hadamard there. Now see, it's starting to rotate by some different angles, so on around the Z axis. So you can play with that. And this is just how you can do any general unitary, and you see the notation here. Shows you unitary with theta phi lambda are drawn on the circuit. Oh, okay. And we know this will not work. I'll leave it to you as an exercise. Replace this. Okay. You should just be able to cut and paste from the earlier parts where we fixed the code. Okay. Okay. That's it. That's it for single qubit gates. So I just wanted to go back and do single qubit gates in Qiskit. Now you know how to do it. You can simulate your own stuff. You can, of course, we did everything with the regular simulation, but in the previous class, we introduced also how to actually submit this as a job to the quantum processor. I don't recommend trying to submit single qubit gates to the quantum processor because you're just going to be waiting for a while for like a very simple thing, which is a single qubit gate result, which is not very interesting in some sense, right? We can always simulate that on our classical. But very easy. So, all right. Okay. That's it. Any questions so far on the single qubit gates? Let me see if there are any of the other gates notebooks. So it sounds like none of the notebooks I sent you are going to be working. No, this one apparently loaded. Huh. Oh, no, it didn't. Okay. Just made me fooled me for a second. Okay, so we're gonna have to launch it again from the textbook, which is fine. Now you also know how to get to the textbook. So this one is under chapter gates, multi-qubit stuff. Okay. All right, so now we go through the same exercise on Qiskit with multi-qubit gauge. I'm not going to go over the math of this. We've gone over it so many times in class. So I'll just like quickly show you now again how we are just, representing the different qubits and so on. This is just the same imports as before. Okay, and then this draws a quantum circuit with 3 qubits and a Hadamard on each one of the 3 qubits, as you can see here. So 3 qubits, 3 Hadamards on one on each of the qubits. That's basically what you expect. And so each of them is in the plus state. So that means that the output vector will look like this, right? Basically, it's just all of them are in the plus state. So there's a uniform superposition of every single string 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, etc., up to 0, up to 1, 1, 1. So that's what labels each of these, just like before, 0, 0, 0 up to 1, 1, 1. So that's what we will get. And okay, here again, we have the same issues that we've already encountered. So we can fix it by just looking at our code here. So let me do at least the first one. I guess since I fixed it, I should remember, but I don't remember what I did. That's just the part here. So all that really happens is that instead of this run Q obj, which we don't need anymore, we just need sim over here and then get the state vector. And we can't really, we can try to plot it, but I suppose. Oh, one useful thing here, which I think is somewhat helpful. I don't know if this will work, so we'll run it and we'll see, is from the visualization package, there's something called array to LaTeX. And that is helpful because it just prints out the state vector and so on in a nice form, as you can see here. And okay, if you know a little bit of LaTeX, then this will make sense to you. If you don't, it's fine. You just need to know that if you want some text, you can do this, but you can also include equations and things like that in here using LaTeX formulas. So just something, if you're interested, you can explore the array to LaTeX function. And and the other thing I should probably show you is where you can find more information about all this. Let's see. I think I had that. Yeah, so this is the Qiskit documentation. So if you just search for Qiskit documentation, you can find basically the entire, all the classes and their functions and everything is in here. And so you can look up what any particular function does by just coming here and looking. So for example, save state vector. And that brings up what that's doing here. Okay. Okay, back to our sample. Okay, so let's see if this will run now. I don't need this line. See. Backend is not fine. That's because earlier we already run that backend.
Just have to replace the Q object with QC.
Yeah, and instead of doing whatever it was doing, QRVJ, it basically what it was doing earlier was taking the circuit and assembling it into what's called a transpiled circuit. Transpiled just meaning that the circuit that you give it may not be what it actually executes in the quantum processor. That's because you may tell it, let's do some gate, like a swap gate or something like that. And actually on the quantum processor, it can't directly do the swap gate. It has to do like a few C naughts or something like that. That's just one example of, things that it might require to change what you've written to what it can actually execute on the hardware. This is kind of what your computer does too, right? It takes your high level code and breaks it into like what assembly language instructions that it can actually do on that processor. For example, if you compile your code on C++ or something, then it's basically converting that to the right machine code for your computer that it's running on, or with Python, whatever, any high level language has an interpreter or compiler. In the same way, this one has this backend when it's before it runs it, it converts it to a transpiled circuit and runs it. Of course, in this backend, it is just a simulation, so it's even easier than regular. But yeah, in the end, it's the same idea. You have to tell it to run it. In the old ways, because you had to go one more step, which is to assemble. That has been removed, I guess, from the later versions. No state vector for expert. Okay.
We just start running from the beginning because it loses
Well,
some
could be. Yeah, all right, let's go back. Yeah, it looks like things here. Starting again. Uh, Okay. I'll look up what's going on here. Some things have obviously changed from the version. Yeah, so. We're out of time, so I don't want to spend time here. I'll figure it out and let you know what's going on there. But everything else is the same, I suppose. We will figure it out. Have a good weekend, everyone. Yeah. No, okay. Not really. I'm introducing this so that you can start doing. I mean, when you do some projects, which you have a final term project, so you may need to like learn some a little bit more there. Like
Yeah.
hope we'll be doing it in teams, so hopefully one of your teammates can like show you a little bit of the Python stuff. Yeah. Yeah. Not yet. You shouldn't need a lot.
Okay.
I mean, you were able to follow along with this code, right?
A little bit.
It should be fairly high level like this,
Okay.
basically.
Thank you.
Yeah, you're welcome.
I'm sorry. Yes. Can I ask you?
Yeah, sure. Yeah. Okay. Yeah.
Is there any like, little ones?
Well, I think we talked about that at the beginning, that
Right.
that the a gate in quantum computers is like a reversible gate in a classical computer. So if you take a classical AND gate, right, which you know from classical computing, you have to make it reversible to run it on a quantum computer. But once you do, you can run any gate that's in a classical computer onto a quantum computer.
So this is really what build
But
here.
yeah.
It's like the instructions in the processor.
Yes.
Okay.
Exactly. And so these gates are like the instructions for the processor, but they're also in some way the algorithm, as we'll see.
That's yeah.
Yeah, when we get to algorithms, we'll see that an algorithm is just some quantum circuit that gets executed on the processor.
Okay.
Yeah.
So for example, on the previous exercise,
Yeah.
you ran the circuit onto the quantum simulator computer at like 1,000 times, right?
Right.
And then you got the one state with a higher probability.
Yeah.
Versus the other state.
Correct.
So what does that mean? What
Well,
does it mean?
I mean, it just means that this circuit is working correctly, I guess. I'm not sure what your question
Like-
means.
Like,
We've talked about how quantum things aren't deterministic.
correct.
So when we,
That. But for me, to understand this, and I just cannot, it's still very visual, I mean,
Mhm,
it's
yeah,
very abstract.
Yeah.
They want to make it practical.
mhm.
How, like, so what if I measure, I knew it was gonna be,
Yeah,
the probability is gonna be 1.
yeah.
So what does that give me? Like, how can I use this
To
in the
solve
next
some.
thing? Yeah,
Well, we haven't talked about that, but I mean, you remember when we discussed the quantum bomb detector, for
yes,
example?
yes,
So I was just trying to show you there that even though it looks like quantum computers are probabilistic, we can run them in a way that we can get more information than a classical computer could get from that situation. But there are only specific situations where a quantum computer will be better than a classical computer.
right.
Not every situation calls for a quantum
Right.
computer. So, but yeah, I mean, it's just, this is the way quantum computers work. They don't give you a deterministic result. They give you a probabilistic result. And from the probabilities, you have to infer something about the system. So maybe when I start the next class, I had started this at the end of the last class, which is I did something called the Ramsey X circuit.
Mhm.
And I wanted to go back and go through the single qubit gates on Qiskit more carefully, because I realized as I was doing it that it might have been going too fast for most of the students. So I did it. I came back to here, to this notebooks in the Qiskit textbook, to show people a little bit more, at a lower level, how these gates work. So in the next class, I'll come back to the Ramsey X circuit, and there we'll see that we can use the Ramsey X circuit to, for example, find some unknown phase, even though we get only probabilistic information. So I'll do a more practical application there. So imagine you are given a box, and what the box does is it puts a phase onto your qubit, okay? You don't know what phase it is, okay? And you have to find out using the quantum circuit what the phase is, okay? So that will be the circuit. I started talking about it in the last class, but I didn't finish that loop because I wanted to come back after we had done these single qubit gates and then come back to that.
Okay.
Yeah.
And then how do you think you're gonna short